Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that we had spent the last few lectures discussing on the non-mean variance framework, and in today's class we start off on a new broader topic, namely optimal portfolio and consumption. And in this we will talk about both the optimal portfolio as well as consumption in the setup for discrete time models as well as continuous time models. And this is the point we will go back and refer to one of our earlier lectures when we had talked about the binomial model and we had talked about the geometric Brownian motion model. So, let us begin this lecture, and the first topic that we will do is, so this broader topic is optimal portfolio and consumption. So, we begin with the first topic, that is portfolio and wealth process, and as I said that we will discuss this in the discrete and continuous time framework. So, we will start off with discrete models. So, let us consider a market model with n risky securities or stocks which are designated by capital S1, capital S2 all the way to capital S of n, and the market has a bond B. Further, let the value of the positions at time t be denoted by x of t. So, this means I will have things like S1 of t, S2 of t all the way to S of capital N t and B t. Further, the assumption is that the initial wealth level or amount be x 0 is equal to some small x. So, what I mean is basically now to be more explicit here, x of t will denote the wealth level at time t when you have started off at an initial time t equal to 0 with a wealth level of x. And in a synonymous manner we will use S1, S2 of t all the way of Sn of t, Bt to denote the price of the stocks and the bond at time t. So, let us now get focused on what is going to be my wealth process x of t subject to us having started off with the initial amount to be invested as being some little x. And this initial amount is invested in the capital L number of stocks and bond. So, we now consider the problem in the single period framework. That is, trading happens at say time t equal to 0 and t is equal to 1. Now, let delta I denote the number of units of stock Si at time t equal to 0. So, that means at time t equal to 0 you purchase delta I number of the stock Si, and this is held till, so I should say that this is purchased at time t equal to 0 and held till time t equal to 1. And let delta naught denote the number of units of bond B purchased at time t equal to 0 and held till time t is equal to 1. So, the assumption is that there are no transaction costs. All right. So, now once we have this set up, what we can do is that we now can introduce what is known as the self-financing condition. So, accordingly, the self-financing condition is given by x 0 is equal to delta naught b 0 plus delta 1 s 1 0 all the way to delta n s n 0. And the wealth at the end of the period is given by x of 1 is equal to delta naught b 1 plus delta 1 s 1 of 1 all the way to delta n s n of 1. So, what do you have here? So, basically we start off at time t equal to 0, we start off with the wealth level x 0 equal to x, and this at time t equal to 1 has the value of x of 1 given by this relation. So, how do you get x 0? So, remember that you have invested in delta naught number of bonds at time 0 and you have invested in delta I number of stocks S I at time 0. So, that means that this expression here, this is going to be the total investment that you have at time t equal to 0, and this must exactly match the amount of money that you have in hand, namely x of 0. Now, remember that these delta naught, delta 1 all the way to delta n, these are positions that you get into at time t equal to 0 and hold on to until time t equal to 1. So, accordingly, the wealth at the end of the period is given by, so delta naught into the price of the bond at time 1, which is b 1, and then all these delta i's with the price of the stock S I being S I of 1. So, you add this up and this will give you the value of your investment or the value of the portfolio at time t equal to 1. Okay. So, this is called the self-financing condition, because that you can only invest, the total investment must exactly match the amount that is available in hand. So, that means that the whole investment of delta naught, delta 1 to delta n must be completely self-financed by the money that is hand without any external support. Okay. So, now what we introduce is, we introduce a notation of this to club together delta naught, delta 1 all the way to delta n, and we call this vector delta. So, this is the vector of positions delta as given here. This is called the trading strategy. So, what we do now is we now introduce the notion of consumption as an individual economic preference. So, accordingly, as a result of the introduction of the concept of consumption, we revisit the wealth equations to account or incorporate the consumption. That is, consumption means spending money outside the market under consideration. So, remember what is the market under consideration? The market under consideration was the bond S1 all the way to Sn, and consumption means that, so if you are in the market under consideration, that means that your investment will be in the bond or one of the bond or S1 or S2 all the way to Sn or a combination of that. So, consumption is basically spending money not on any of these what we call securities, that is the bond and capital and number of stocks, but spending the money somewhere outside the market for the purpose of your individual consumption. So, here this basically means that the amount that is consumed is no longer in circulation in the market under consideration. Alright, so let then we introduce a notation. So, let C0 denote the amount consumed at time t is equal to 0, and another notation we introduce is let x of 1 denote the wealth prior to consumption at time t is equal to 1. Now, let us now re-examine the self-financing condition after consumption. So, accordingly, the self-financing condition becomes, so earlier what we had? We had delta naught B 0 plus delta 1 of S 1 of 0 all the way to delta n S n of 0. And earlier this was equal to x of 0 is the wealth that is available at time 0. However, now that you have made a consumption of C0, that means this amount of money has gone outside the market. So, the remaining amount that you have is the one which you can invest in the market, and then x0 minus C0 must be equal to the amount invested in the market after the consumption C0 has happened. And also the wealth prior to consumption as indicated in the preceding line of the previous page. So, the wealth prior to consumption at time t equal to 1 is given by, as before, x1 is equal to delta naught b1 plus delta 1 s1 of 1 all the way to delta n Sn of 1. So, thus in general the wealth process before consumption at time t is given by x of t is going to be equal to delta naught of t into bt plus summation delta I t into S I of t, I is equal to 1 to n. So, we now enumerate the conditions that need to be applied on the portfolio process capital X of t and the consumption process. So, remember the consumption is also a process, you can consume at the time generic time t, and these conditions are driven by both mathematical and economic considerations. So, let us enumerate these conditions. So, the strategy, and by strategy I mean here C as well as the vector delta of the investment, this is admissible or that is allowed if, so this is something like opportunity set that we have done, if C of t is a non-negative adapted process. And let me explain what adapted process is. So, this means that, in other words, C of t is dependent on the information available at time small t. Secondly, bankruptcy is not allowed, which mathematically translates to the following, that the wealth at time capital T must be greater than or equal to C of capital T. So, that means your consumption at time capital T cannot exceed your wealth level at time capital T. And thirdly, the self financing condition is given by the following. So, let us look at time t. At time t, you have a wealth level x of t, and then you have consumed C of t, and the remaining amount you invest in bonds, delta naught bond, delta 1 in the first stock, all the way to delta of n S n of t, and this delta naught will have the argument t plus 1 to indicate that this is an investment made at time t and held up to time t plus 1. So, likewise delta 1 t plus 1 all the way to delta n t plus 1. Okay. Okay, so what we had actually here is that this delta naught of t, this is basically the investment made at time t minus 1, and this is the investment made at time t minus 1, and this is the number of units that you hold at time t till time small t, and then the value becomes delta naught of t into bt and summation of delta I of t S I of t, and this ends up being the value of your holdings at time t given by x of t. So, please understand that this is the investment made at time t minus 1 held until time t. So, likewise here this one is the investment that is made at time t, and likewise these values, but held until time t plus 1. So, for delta x, the argument will indicate the time point till which the investment is actually being held. Okay, so now what we do is that we now elaborate on consumption choices. So, accordingly, let x denote a consumption choice, and x could be basically a different alternative investment that you have, or different consumption alternatives that you have. Now, if the consumption choice x1 results in, so this x should not be confused with the self financing condition. So this should be, this is synonymous with C. So this results in more money being generated than the consumption choice x2 under all states or circumstances. Then we say that x1 dominates x2, and we denote this by x1 being greater than or equal to x2. So, this is the notation. It is not literally greater than, but this is the notation. Now, unfortunately, the reality is slightly different, as we had seen in case when we were discussing SSD, FSD and TSD in the previous class. So, in reality, what happens is that in some states, so this is similar to when we looked at the cumulative distribution of one being greater than other in some range of R, and the cumulative distribution of the one being less than the other in some other range of the returns. So, a similar kind of argument will now result in the following statement, that in reality in some states or circumstances, one choice will result in more money, and in other state or circumstance the same choice will result in less money. So, obviously, this brings us to the question of how we can make a consumption choice. So, the next thing we will look at is comparing consumption choices. So, the first topic is the first sort of axiom or comparative criteria is the following, that if the investor likes the consumption choice x1 as at least as much as x2, this is denoted by this notation. Secondly, if the investor always likes x1 choice x1 to x2, it is denoted by this notation. And thirdly, when the investor likes choice x1 as much as x2 and x2 as much as x1, the investor is indifferent between the two choices x1 and x2, and this is denoted by x1 similar to x2. So, this brings me to the properties of preference relation and we will enumerate 4 properties. So, the first property is completeness or some sort of exhaustiveness, and this is stated as given any 2 strategies x1 and x2, we have either, so there are only 3 possibilities, that x1 is at least preferred to x2, or x2 is preferred to x1 at least, or possibly both. Next is transitivity. So, if the consumption under x1 is preferred over x2, or at least preferred as much as x2, and x2 is at least preferred as x3, then this preference will hold for x1 over x3. Thirdly, this is monotonicity. So, if x1 is preferred over x2 in numerical terms, then the consumption x1 is preferred over x2. And finally, we have the condition of convexity. So, in this case what we do is that we start off with 2 consumption x1 and x2, and we consider the consumption choice x3, and that is given by some linear combination alpha x1 plus 1 minus alpha x2. Of course, alpha strictly lies in the open interval 0 1. Then we have x3 is preferred over x whenever we have x1 is preferred over x and x2 is preferred over x. Let us now consider an example of comparing consumption choices, and you look at 2 scenarios. So, scenario 1 is enumerated as follows, and in scenario 1 the investor has to choose between 2 projects. The first project is that, so project A pays either 10 or 100, and there is a project B pays 15 when A pays 10, or it pays 110 when A pays 100. So, under the circumstance that A pays 10, then B will pay 15, which is a higher amount, and in the circumstance when A pays 100, then B will pay 110. So, in both the cases, both the scenarios, B will pay more. So, thus the obvious choice is to invest in project B. Alright, so let us look at another scenario, slightly different, where you are caught in a dilemma. So, here again project A pays as before, here it pays either 10 or 100, but project B pays 110 when A pays 10. So, that means it pays more, and it pays 15 when A pays 100. So, in this case B pays much less. So, under one circumstance B will pay more, in another circumstance B will pay less. So, accordingly in this case it is not clear whether A or B should be the choice. So, this brings us to revisiting utility functions in the context of consumption. So, recall that the utility function maps the consumption choices to real numbers. Remember, we had introduced the term called utils, and that is, it assigns a real number to every choice of consumption, which helps in determining preferences between different choices. So, accordingly, if u of x 1, that means the util of x 1 is greater than or equal to that of x 2, this will imply that x 1 is preferred at least as much as x 2. If u of 1 is strictly greater than u of x 2, then it implies that x 1 obviously is preferred over x 2, and if u of x 1 is equal to u of x 2, this means that the investor is indifferent to the two choices x 1 and x 2. Alright, so when we talked about utility functions, we had sort of assumed that we have a wide range of choices of utility functions. We talked about log utility, quadratic utility and so on, and we had used this in several contexts. So, what you are going to do now is going to look at a very simple example to identify how to figure out what is going to be the utility function for each individual investor. Now, this is actually a non-trivial exercise, but we just give an illustration of a very simple way of doing in a very particular case as mostly as an illustrative example. Of course, in reality it is going to be very difficult to extend such kind of situations in general when you are looking at a person specific utility function, at which point you have to mostly rely on whether the person is risk averse, risk neutral or risk loving, and accordingly you can make a choice of utility functions. But what we are going to do now is look at a very specific example of how one can determine the utility functions based on very specific inputs from the investor in terms of their preferences. So, accordingly we look at this example on determining the utility. So, what happens here is two investment opportunities are offered to an investor. So, what is the first opportunity? In the first opportunity, at the investment pays an amount of 10,000 with certainty and in the second opportunity it pays. So, the second opportunity, the first one is a deterministic quantity and it pays a certain amount. So, this is like a bond, and the second opportunity is going to pay out random variables. So, it pays out 3 possible values, 22,500 with probability 0.3, 4,900 with probability 0.3 and an amount of 900 with probability 0.4. So, in order to establish her or his preference, the investor takes the power utility of the form ux equal to x raised to gamma 0 less than gamma less than 1. As a result, the utilities from the two investment opportunities are given by the following. So, the utility ux is equal to x raised to gamma. So, then we look at both the opportunities and what is going to be the utility. So, in the first case for opportunity 1, I will denote the utility as u of 1, and this is going to be simply, so here 1 does not indicate the value, but this is going to indicate the opportunity 1, and this is going to be nothing but the wealth level 10,000 raised to gamma. And in the second case u of 2, that is the utility for opportunity 2, this is going to be given by the expected value. So, in this case it is going to be the expected utility, and this will be given by, so we had the values 22,500 and the utility is this value raised to gamma multiplied by the probability of 0.3, plus we had 4,900. So, we had 4,900 raised to gamma multiplied by the probability 0.3, plus we had 900 the utility of which is raised to gamma multiplied by the probability 0.4. So, these are going to be the utilities for the first opportunity and the utility for the second opportunity. So, this brings me to the question as to what is the value of gamma. So, unless I know the value of gamma for the investor, I cannot make a comparison between u1 and u2 and hence cannot establish a preference criteria. And the goal is, so accordingly the goal is to determine the value of gamma. Now, in order to determine this value of gamma, we need more preferential information from the investor. So, then the investor says that they are indifferent. So, that means in this case the choice of gamma is driven by the indifference of the investor to a choice of either receiving an amount of 100 for sure or